Alright, thank you for tuning in to another physics lesson with Mr. M. In this video lesson, I'm going to be basically putting together all of the different types and topics of forces that we've been talking about thus far. So things like free body diagrams, apparent weight, coefficient of friction, and interacting objects. We're going to kind of put it all together in this one problem, and we're just going to take it step by step and solve for it. So here we have our problem. We have our two blocks that are connected on a string. We're on an incline. Mass 1 has 20 kilograms. Mass 2 is 5 kilograms. We have a coefficient of kinetic friction of 0.2, and the angle that we're working with is 50 degrees. And we want to know, what is the tension in the string when the objects are moving? So conceptually speaking, mass 1 is 20 kilograms, mass 2 is 5 kilograms. We know that this block is going to be accelerating downwards. And as it's going downwards, this block will be accelerating up the incline. We know that because they are interacting objects, their accelerations are going to be the same. So we will try to use that to our advantage as well. Okay, but the first step, and this should be your first step for all types of force problems, is draw your free body diagrams. Okay, and so for our mass 1 here, we have two forces. We have our weight force, which is mass times gravity, and we have our tension force. We also know that this object is going to be accelerating downwards. For the free body diagram for mass 2, I'll put that in green, we have our weight force, we have our normal force, we have our x and y components of gravity. Don't forget that. Whenever you have an angled vector, you need to break it into its x and y components. And so our angle theta is always in between our y-axis and our weight force. So let's give these vectors their equations, because this vector is adjacent to angle theta. This one right here is going to be mg cosine theta, and this one right here is going to be mg sine of theta. We also have our tension force, and we also have, put it in red, we also have our frictional force, because we do have a coefficient of friction. Alright, so those are the free body diagrams. While we're here, because we have a frictional force, we have an equation for our frictional force, which is mu Fn. Our normal force vector is equal and opposite to mg cosine theta. So our Fn is really mg cosine theta. So let's just take care of that right now. Fn is mg cosine theta. So we're going to just, by substitution, plug that in. So our frictional force is equal to mu mg cosine theta. Okay, now that we got that taken care of, all of our vectors are taken care of. They basically all have some sort of equation to them. So our next step is, let's solve for the net force. What is going to be the net force of this problem here? Well, our net force basically is going to come down to this weight force minus the tension. Well, we don't want to say minus the tension, because what happens with these two tensions? The tension in the string is the same. So this tension and this tension become equal and opposite. So they essentially go away. The tension forces, they go away. We know that this normal force and this mg cosine theta, they go away. So what are we left with? We're left with the weight, and opposing the weight is mg sine theta and the frictional force. So our net force equation is really m1g minus m2g sine of theta minus the frictional force, which we said was mu m2g cosine theta. Alright? That's our net force. How is that going to help us solve for the tension? Well, if you remember, we can use the apparent weight to find the tension. So because this block is going either straight up or straight down, we know that it's going straight down, we can use the apparent weight formula to solve for the tension. So really, the tension in block M1 is going to be M1G plus or minus MA. Well, it's accelerating downwards. So when it accelerates downwards, we subtract. That's how we're going to solve for the tension. To solve for this tension, though, we need to know what is going to be the acceleration of these blocks. How are we going to solve for the acceleration? Well, we have our net force. We just need to divide this net force by the combined mass, right? A is equal to F net, the net force divided by the mass. So let's take all of this and divide it by the masses. So our acceleration is, and I'm going to start plugging in values now, m1 times g, so 20, I'm not going to have enough room to write all my units, so 20 kilograms times gravity, which is 10, minus m2, 5 kilograms, times g, which is 10, times the sine of 50, minus mu m2, and let me just go ahead and erase this and write it. We know that A is F net over M. So let's go ahead and give myself enough room for this. I apologize for that. So once again, 20 times 10 minus 5 times 10 times the sine of 50 minus mu is 0.2 times 5 times 10 times the cosine of 50. All of that divided by both masses since they are connected. So 20 plus 5. When we do this, when we plug all this in, our acceleration comes out to be 6.21 meters per second squared. Now that we have this acceleration, we can plug it into our equation over here. So the tension is equal to 20 kilograms times gravity minus 20 times an acceleration of 6.2. Tension comes out to be 75.8 newtons. Okay, and there you have it. So this combined just about everything in the previous videos, and really the whole problem is set up by drawing your free body diagrams, figuring out what forces cancel out. There was a little bit of substitution with our frictional force equation, but we found this net force equation by knowing that the tensions canceled out. So it was just this weight force subtracting this mg sine theta and this frictional force. We divided all of that by the combined mass to get our acceleration. We plugged in our acceleration to our apparent weight equation. And the reason why we were able to use our apparent weight equation was because this object was traveling downwards. So when we travel downwards, we subtract our weight minus the mass times the acceleration. We showed that mathematically to get our answer. And so I hope that this video was helpful for you. Keep in mind, apply these skills and you should be able to solve any of your force type problems. Thanks for tuning in.